Technology is reshaping the world faster than ever, and advanced health technology helps you make sense of it. We will focus on what it says about data and technology. Stay with me, the best part is near the end. Chapter 1: Tackling Barriers to Rapid, Exponential Acceleration of Advanced Technologies. What to know about data transformation for advanced technologies in medicine. William C. Harding, Florence D. Hudson, Shantanu Chakrabarty, and Sherry Duville. 2 Closing knowledge gaps, critical in advanced technology for medicine, building shared knowledge to drive down risks in medical technology. William C. Harding, Victor Sinzig, Craig Hipps, Neil Petroff, David Rotenberg, Brittany Partridge, and Sherry Duville. 3 Tech misinformation and medical misinformation as evil twins. The misinformation path to destroying trust in medical technology. Sherry Duville, Michael DeCourt, and Kate Liebolt. Chapter 2: Management and Leadership Competencies and Objectives for Driving Allyship in Reducing Medical Technology Risk. Why partnerships are vital to your professional success. William C. Harding, Mike Ng, Brittany Partridge, and Sherry Duville. 5 Extinction is imminent without effective transformational leadership, closing leadership gaps that prevent execution. William C. Harding, Michael Ng, Brittany Partridge, and Sherry Duville. 6 Ignore the dangers of hubris at your own risk. Mitigating the barrier to trust and respect for high-performing teams in medical technology. Karen Jo Madsen and Sherry Duville. 7 Humility as a core value for the adoption of technology in medicine, building a foundation for communication and collaboration. Brian D. Macbeth, Brittany Partridge, Arthur W. Duville, and Felix Enkel. 8 Burnout in Information Security, the Case of Healthcare. Mitch Parker. Chapter 3: How Cybersecurity Enables Deployment of Advanced Technologies. Security Frameworks as a Foil for Larger Management Issues. Mitch Parker, Brittany Partridge, and Allison J. Taylor. 10 Managing Third-Party Risk, Framework Details for Risk Management in Medical Technology. Mitch Parker, Brittany Partridge, Eric Svetkov, and Allison J. Taylor. 11 Hospital at Home, Managing the Risks of Delivering Acute Care in the Patient's Home. Mitch Parker and Peter McLaughlin. Chapter 4: The Practical Technical, Legal, Management, and Leadership Steps. Mitigating Value Risk in Innovation, a physician product design expert's lessons learned driving clinical product development. Joshua Tamayo Sarver. 13 Playing with FHIR, the path to ensuring we bring the power of supercomputing to how we understand healthcare in medicine. Lucia C. Savage. 14 Technology and the Engaged Patient, Evidence-Based Patient Engagement for Improved Patient Outcomes. Lucia C. Savage. 15 Interoperability and Information Blocking, How to Enable Data Sharing and Keep HHS Happy. Peter McLaughlin. 16 The Role of Standards in the Responsibility and Rewards of Medical Technology Industry Leadership. Identify your objectives to build your path in leading the future of medical technology. William C. Harding, Ken Fuchs, Mitch Parker, and David Rotenberg. Closing Thoughts. Appendix A. Glossary of Key Terms. Brittany Partridge. Index I. Tackling Barriers to Rapid, Exponential Acceleration of Advanced Technologies in Medicine. Chapter 5, doi 10. Introduction. What is data transformation? Data transformation in healthcare. EMRs and EHRs in transforming data. Definitions and terms. Need for data transformation in healthcare, where quantum computing can make a difference. Cybersecurity and quantum technologies for healthcare. References. Introduction. Data transformation means different things to different people, and if you aren't aware of what data transformation means in your business, then continue reading as we seek to characterize it in relatable terms. For example, transforming data can be related to applying additions, subtractions, encryption, compression, interpretation, masking, and even the existence of corruption. Data transformation is also a key point to keep in mind as you think along the lines of technology integration, interoperability, and data aggregation. But even more importantly, when you think about data transformation, you must be looking through the lens of data integrity and data security. That said, this chapter will provide you, the reader, with a solid overview of what is data transformation, with an emphasis on considering data transformation within medicine/healthcare/life sciences. What is data transformation? According to Augustine, 2017, the transformation of data occurs between a multitude of dissimilar solutions. With that in mind and in consideration of the issue of disconnected healthcare technology, it is proposed that there is a need within healthcare communication solutions, interactions between humans, hardware, and software, to function and exchange data interoperably across dissimilar models/foundations, where, according to Venegas, Fernandez, and Maldonado, 2016, interoperability represents securely transforming data using standardized interfaces, Cook et al. 2016, Janaswamy and Kent 2016, Cohn, Topologlu, Kirkendall, Darrad, Wells, and Gherkin 2022, Steegman and Gersh 2021, Wager, Lee, and Glazer 2021. Specifically, the need that is being described is the ability for solutions to securely exchange data between all elements of healthcare environments, facilities, and organizations using standards and practices that promote seamless error-free data transformation. Whereas, the transformation of data is a process that should occur between all components of a healthcare environment, which involves the interconnection of dissimilar elements, people and technology, such that data is received, shared, and processed. Dioran et al. Data transformation in healthcare according to Cook et al. The issues associated with healthcare solutions not being able to seamlessly transform data between dissimilar technology is rooted in the processes associated with assessing, integrating, and sustaining new technology into healthcare environments. Accordingly, the issue of needing seamless data transformation represents a gap in existing technology adoption models to examine the perceptions of all relevant stakeholders as their technical experiences potentially influence assessment, decision-making, adoption, and sustainability of transformative technology. Cook et al. 2016, Dagfus, Belkaja, and Ahmad, 2018, Ingebrigtsen et al. 2014, Liba, H. Sears, and H. Pner 2015, Peterson 2018, Van Oorschot, Hoffman, and Hellman 2018. Specifically, the ability to transform data is presently accomplished using methods such as non-standardized electronic healthcare/medical records, EHR/EMR, and data protocols that connect the vast array of dissimilar healthcare components. Transforming the data from the point of collection to the point where it is used to make health-related decisions requires that human errors are not present and where solution response time could literally mean a patient's life or death. Coneth 2016. Furthermore, and according to Mandel, and Kohani, 2015, variability between solutions is an issue where the absence of a standard communications method for transforming data will result in data instability across the multitude of dissimilar technology. EMRs and EHRs in transforming data in using EHRs/EMRs to solve the issues of data transformation between dissimilar technology. The healthcare industry is attempting to connect technology using a solution that was created for the purpose of addressing billing issues. Zhang, Abraham, Novak, Reynolds, and Gettinger 2016. That approach compounds the problems, where healthcare professionals act as the interface between dissimilar solutions, creating a greater potential for human error as they manually collect and transform/transcribe the data into a usable format. As suggested by Mendel, and Kohani, the inability to establish the basic foundational element of what is described as a transformational engine, using standardized input, output, and functional modules, exemplifies the conditions that will result in continued increases in healthcare-related costs and decreased patient care. Kraus, Schiavone, Pluzhnikova, and Invernizzi, 2021, suggested that healthcare environments that can successfully integrate transformative technology will be able to seamlessly transform data across dissimilar technology and ultimately provide improved patient care. The point of data transformation emphasizes that there is a need for the healthcare industry to consider technology integration from a higher level, where the adoption of transformative technology represents a potential for improved therapeutic outcomes, reduced human error, and sustainability within the scope of adaptive solutions. Definitions and terms. Transformational engines. A transformation engine is a principal element that encapsulates other elements, input and output connectors, that are used to transform data within a technology solution from one format to another format using specific data mapping rules that are defined in the engine's configuration module. Input connectors. An input connector takes data that enters a transformational engine through a data queue and stores the data in a data stream to be processed separately by the execution layer of the engine. Within the scope of this discussion, an input connector is an element of a transformational engine, which facilitates the transfer of data between dissimilar technological solutions. Interoperative. It is the ability for humans, hardware, and software technology to connect and communicate using a standard protocol, where data may be transformed across dissimilar technology. Wager, Lee, and Glazer 2021. Technology that is considered interoperable represents solutions that are able to connect with other technology and exchange data using standardized protocols through a common interface such as is characterized by a transformational engine. That proposal is supported by the material presented by Evans et al., 2017, and Slight et al., 2015. That showed technology cannot be considered as successfully integrated within an environment if that technology is incompatible with existing technology. Output connectors. Output connectors take data that is changed into a different format by the transformational engine and pushes that data into queues that pass the data to designated target locations. Like the input connectors, an output connector is an element within the concept of a transformational engine, which facilitates the transfer of data between dissimilar technological solutions. Input-output connectors and transformative engines. Input and output connectors were designed around an internally developed transformative engine that is adaptive in its ability to connect dissimilar technology and transform data using a defined set of configurable rules. Data and solution control within the transformative engine are then securely managed through a standard interface layer where it is received, processed, and transmitted in accordance with the established rules. Furthermore, the transformative engine is designed such that it can use instructions that are carried with the data to adjust any predefined rules and influence the processing of data through a method described as bidirectional metadata encapsulated token authentication. Paffel and Harding 2018. The data specifically acts as the controlling element, a virtual messaging bus, that determines how it will interface and transform between dissimilar technology and across a standardized interface layer. Macarola, Albano, Ferreira, and Teixeira 2016. Need for data transformation in healthcare. There is a need to examine more than just the potential benefits associated with adopting new technology, where technology adopters must consider the risks of misuse as well as the ability to secure any and all data that is transformed across new technology and existing technology. Accordingly, Kanath proposed that the added burden associated with collecting, controlling, and distributing data must be factored into the assessment and decision-making phases associated with technology adoption. That said, and within the scope of manufacturing environments, there is a need to deploy technology solutions that work interoperably with existing systems, such that seamless transformation of data is needed. Thus, the results of this discussion can be used to reinforce the need to consider technology interoperability in earlier phases of project planning and not just at the point when technology is being deployed. Where quantum computing can make a difference. Quantum computing has real-life applications in that it is exponentially faster than traditional computers when working through algorithms. This means it can tackle big data problems with large probability sets more efficiently, like effects of chemicals in drugs, financial trading, and analysis in quantum chemistry, to name but a few. The use cases of quantum computing in these problems are still under development, but new algorithms yielded by quantum computing will accelerate the rate at which these big data problems are resolved. In quantum networking, the goal of post-quantum cryptography is to develop systems that are secure against both quantum and classical computers. Financial institutions are leading the way for secure quantum networking because of the clear importance of secure transactions at both ends and even in between. International aerospace teams are conducting quantum experiments dedicated to quantum use in satellites, enabling faster data transfer and better data encryption. And some countries, such as Switzerland, are even using quantum networking to secure voting and protect elections. The bottom line is that quantum computing is the next big thing in computing. We just have a few hurdles to surmount before it becomes any better than traditional computing. Quantum networking already has such high demand because current encryption methods are always under active threat. Specifically, the need for quantum computing is likely to grow in the coming years, but more as a complement to investments in things like exascale computing that performs at least 1 quintillion, 1 billion, calculations per second. Bringing those technologies together will unlock tremendous computational potential. Quantum S-power also allows us to process imagery which requires significantly more processing power than traditional datasets at scale. This ability could allow clinicians to more quickly analyze images, such as CT scans, and identify any anomalies, resulting in a faster diagnosis and improved patient care. For example, multi-factor optimization problems. Those are the types of things that quantum will be good at, said Matt Kinsella, managing director at Maverick, the VC arm of $8 billion hedge fund Maverick Capital that has invested in quantum computing technology. In terms of the future of data transformation through the lens of quantum computing, here are a few questions to consider and possibly answer. If data can exist in 2 or more locations at the same time and that data state is mirrored in all locations, how do we apply an equal amount of protection for that data in all locations? We explain this in terms of a prospective IEEE standard definition, TIPS. TIPS and quantum opportunities. Can we trust more in the information and recommendations based on quantum computing to improve responsiveness to a challenging situation, improving trust in the recommendation, which could improve outcomes? Could we improve safety in medical procedures by using quantum computing in real-time healthcare, or leveraging real-time information with predictive analytics and very high-performance computing? Can recommendations be made which could improve outcomes, leveraging more context and experience to be a more expert system to deliver real-time recommendations? Can the ability of quantum computing to assess many images and data very quickly improve predictive analytics for the TIPS elements? Can distributed big data and analytics, injecting quantum, locally or centrally, improve health outcomes? Can different efforts to transform data occurring at the same time but in different locations cancel each other out? Can a quantum bit/byte/word be locked in one location such that no transformation in another location can occur? Can normal data contain qubits? Note, a practical example of qubits. An example of single-state versus multi-state data might be characterized through an examination of a mouse running a maze trying to find a piece of cheese. However, in our traditional and current world of binary data, the mouse would systematically check each path for the cheese and would probably continue checking each path, even after finding the cheese. In contrast, a mouse working in a quantum state would be able to check each path of the maze at the same time. Cybersecurity and quantum technologies for healthcare ensuring data, devices, and humans remain safe in the increasingly digitally transforming world of healthcare is of the utmost importance. While the leverage of advanced technologies can bring great potential value, these technology innovations can introduce increased risk of digital attacks which could compromise privacy, protection, safety and security of data, devices, and humans. We must design security into healthcare devices and solutions from the beginning. As noted in the KPMG report on security and the IoT ecosystem, Hudson, LaPlante, and Amoeba 2018 security really needs to be designed into IoT solutions right at the start. You need to think about it at the hardware level, the firmware level, the software level and the service level. And you need to continuously monitor it and stay ahead of the threat. The cybersecurity community has been increasing its focus and communications regarding medical devices. On January 19, 2016, an open letter to the healthcare community leaders from the security research community was published, Woods, Caravos, and Corman 2019. This letter urges stakeholders to acknowledge that patient safety issues can be caused by cybersecurity issues. Embrace security researchers as willing allies to preserve safety and trust. Attest to these 5 foundational capabilities to improve visibility of their cyber safety programs. Collaborate now to avert negative consequences in the future. This letter is available on the website for the organization I Am the Cavalry, along with a Hippocratic Oath for connected medical devices which includes the following statement: I will revere and protect human life, and act always for the benefit of my patients. I recognize that all systems fail, inherent defects and adverse conditions are inevitable. Capabilities meant to improve or save life may also harm or end life. Where failure impacts patient safety, care delivery must be resilient against both indiscriminate accidents and intentional adversaries. Each of the roles in a diverse care delivery ecosystem shares a common responsibility. As one who seeks to preserve and improve life, I must first do no harm. There are many cybersecurity tools and techniques that can be deployed in connected healthcare, including many types and levels of encryption as explained in the book Women Securing the Future with Tips for IoT Trust, Identity, Privacy, Protection, Safety, Security for the Internet of Things, Hudson 2019. As detailed in this book in Chapter 11, Securing IoT Data with Pervasive Encryption, pervasive encryption is a strategy in which data is encrypted everywhere it travels and/or resides, including data in transit and data at rest, at multiple layers of the computing environment. It is a crucial strategy to enhance privacy and security in our increasingly connected world. There are many forms of encryption. Network encryption, application-level encryption, database-level encryption, file and data set-level encryption, disk and tape-level encryption. There are new technologies on the horizon to secure the clinical Internet of Things, IoT, data and devices, including homomorphic encryption, crypto anchors, and quantum technology. However, homomorphic encryption is designed to provide a means to perform mathematical operations on encrypted data, which when decrypted provides the correct result. Hudson 2019. Just like other forms of encryption, homomorphic encryption uses a public key to encrypt the data. Unlike other forms of encryption, it uses an algebraic system to allow functions to be performed on the data while it is still encrypted. Marr 2019. Only the individual with the matching private key can access the result. Crypto anchors are a blockchain-based technology designed to validate the authenticity of objects, such as pharmaceuticals in the medical supply chain. Hudson 2019, Bulgarusmi et al. Ensuring the authenticity of pharmaceuticals and medical devices is of critical importance in delivering safe healthcare. This type of data or metadata about pharmaceuticals and other elements of the medical supply chain can use technologies such as crypto anchors to add Internet of Things technologies to medical resources such as pharmaceuticals to increase trust, identity, privacy, protection, safety, and security in patient care. Quantum technology is an emerging field of physics and engineering, encompassing technologies that rely on the properties of quantum mechanics, including quantum entanglement, quantum superposition, and quantum tunneling. Researchers are building low-cost quantum-based security solutions which can be applied to improve cybersecurity for healthcare from devices to data and the medical supply chain. One such team from Washington University in St. Louis is developing quantum tunneling-based timer technology. Hudson and Chakraborty 2021, Chakrabarty and Joe 2021, Chakrabarty and Joe 2019. To create self-powered timers with no electromagnetic (EM) signature and therefore no side channels, eliminating risks of intrusion through a power side channel or EM side channel. It is also tamper-proof, whereas if someone tries to manipulate the device physically or digitally, it changes the functionality of the device due to its quantum nature. Uses include creation of a trusted platform module, TPM, key distribution, access control, authentication, and IP protection. The self-powered timer hardware works in conjunction with a dynamic authentication software stack to provide an end-to-end security solution. The team hopes to someday use the timers for securing sensor data in a variety of applications, like monitoring neural activity or monitoring glucose level inside the human body. Advanced technologies can improve the tip's trust, identity, privacy, protection, safety and security of data and devices in connected healthcare and mobile medicine, but there is more to do. The IEEE/ULP 2933 Standards Working Group on Clinical IoT Data and Device Interoperability with TIPS is building TIPS frameworks with technical and process elements to further the state-of-the-art in this area, for today and the future. Professionals from medical device manufacturers, healthcare providers, technology, cybersecurity, academia, and research are working together in the P2933 Working Group and are publishing recommendations to improve TIPS. The book Women Securing the Future with Tips for Connected Healthcare showcases the work of 17 women from technology, cybersecurity, medicine, law, and other domains pertinent to improving tips for connected healthcare and mobile medicine. Hudson 2019. Considerations and recommendations are included related to cybersecurity frameworks, reference models for information assurance and security, and adaptive cybersecurity for existing and future healthcare and organizational needs. Chapter topics include Health Data Management for Internet of Medical Things by Oshani Senaviran, Architecting and Evaluating Cybersecurity in Clinical IoT by Tanya Pavleska, Do No Harm, Medical Device and Connected Hospital Security by Gabrielle E. Hempel, The Case for a Security Metric Framework to Rate Cybersecurity Effectiveness for Internet of Medical Things, IOMT, by Zulema Bellew Caldwell, How Can We Trust in IoT? The Role of Engineers in Ensuring Trust in the Clinical IoT Ecosystem, by Jodin Platt, Sherry Duville, and Mongthavan, The Hospital of the Future in Security, An Arranged Marriage, by Alexis Diamond and Joanna Lynn Grama, The Right Not to Share, Weighing Personal Privacy Threat versus Promises of Connected Health Devices, by Jenny Colgate and Jennifer Maisel. Ransomware, To Pay, or Not to Pay, That Is, One Question, by Melissa Markey. TAP and Intelligent Technology for Connected Lifestyles, Trust, Accessibility, and Privacy, by Catherine, Kit, Grace August, Mathine Selathurai, and Paula Muller. The Rise of IOMT, Leveraging a Policentric Approach to Network-Connected Medical Device Management, by Corey Brennan and Emily Dillon. Editor-in-Chief, Florence D. Hudson. Chapter 6, doi 10. Knowledge Gaps, Technology Integration and Interoperability. Knowledge gaps across cultural and geographical diversity. Reduced collaboration, reducing risks in healthcare. Knowledge transfer use case / example. Space Shuttle Challenger accident results of failed knowledge transfer. Swim lanes, or building team alignment and synergy. Security, privacy, trust, identity, safety, interoperability. A cognitive approach to understanding and motivating knowledge sharing, interoperability, and technology integration. What is the purpose of interoperability in healthcare, and do knowledge gaps affect it? Interoperability summary. What role might AI play in reducing knowledge gaps? Artificial intelligence, AI, in reducing or widening knowledge gaps. What is experiential knowledge? Summary. Human experience and knowledge terms and definitions. References. Knowledge gaps. Knowledge gaps between stakeholders can be costly in business, specifically as those gaps represent misunderstandings or even a lack of understanding of how things might work together. For example, without an understanding of how healthcare data could be used, it is possible that important data is discarded or ignored. Rodriguez et al. Whereas, by listening to the needs of end users, relevant stakeholders, we gain an understanding of how important all data is and how that data might teach us something that we didn't already know. Accordingly, it could be gleaned from those statements that without the perspectives of all relevant stakeholders, we might miss something important, ultimately widening gaps between what is known and unknown. That said, a similar conclusion can be drawn regarding how gaps in knowledge associated with cybersecurity can result in corrupted or compromised data. Thus, a need to reduce knowledge gaps and reduce risks to a business or even a patient could represent the difference between life and death. In considering what data is important, it is also possible for the converse to be true. Data, or at least data relationships, can be considered important, but only leads to further obfuscation. The classic case of this is the confusion between correlation and causation. For example, as cheese consumption increases, more people die by entanglement in their bedsheets. Schwartz and Stanovsky 2022. Finally, we can create new data by fusing information from multiple sensors or building highly accurate user profiles from disparate and unstructured pieces of information. This is a huge business trying to take advantage of every type of footprint we leave in all forms of media. It has been estimated that 90% of all data in the digital universe is unstructured, Cahianti and Permana 2022. The latter is notorious for purposely fomenting misunderstanding and, therefore, increasing knowledge gaps. Data itself can embed bias, and as we massage it more and integrate it into algorithms, which may also embed bias, the overall system bias becomes ever more entangled. For these reasons, practices of data and text mining for prescriptive modeling can be seen as an issue of cybersecurity. Technology integration and interoperability. With a clearer grasp of what is meant by knowledge gaps and the risks associated with knowledge gaps, we examine some of the areas and concepts where knowledge gaps can have undesired consequences. One of those first concepts that receive our focus is technology integration and the subset of interoperability. That said, in this section, we present and discuss the importance of reducing knowledge gaps to successfully deploy interoperable solutions. Intro: Technology integration for the purpose of exchanging and transforming data represents the central theme associated with interoperability. It also represents a concept or model that is not well understood and thus results in considerable knowledge gaps across developers and users that, if not resolved, will lead to failure. That said, this discussion will highlight the current state of interoperability within healthcare environments, the risks associated with current embodiments of proposed interoperable solutions, and things that need to be considered when building an interoperable solution. Definition: Interoperability is the ability for humans, hardware, and software technology to connect and communicate using a standard protocol, where data may be transformed across dissimilar technology. Wager, Lee, and Glazer 2017. Technology that is considered interoperable represents solutions that are able to connect with other technology and exchange data using standardized protocols through a common interface such as is characterized by a transformational engine. That proposal is supported by material presented by the Evans et al. 2017 and Slight et al. 2015. That showed technology cannot be considered as successfully integrated within an environment if that technology is incompatible with existing technology. Summary: Technology integration and interoperability. Interoperability may not be an obvious point to consider when we speak in terms of reducing knowledge gaps, but in the healthcare and life sciences world, the issues associated with ill-conceived transfer of knowledge/data/information do in fact represent a major barrier to successfully reducing knowledge gaps. So, as we think about the elements, behaviors, and methods associated with creating successful interoperability, we need to consider how a lack of vision toward data and technology interoperability represents one of the biggest barriers to the successful transfer of knowledge. Interoperability example: as the design engineer for a steel producer, part of the job of one co-author of this chapter was to approve orders based on production capabilities and assign a predefined process flow. Orders entered into the fulfillment system were planned out by when the product would be at a particular process by calendar year week. This is a long process, about 12 weeks or so, including several process steps that may take place as far away as on different ends of the country. Raw materials must be converted to steel, the liquid steel must be cast, the cast slab must be rolled, and so on until the final product, output from the steelmaking process, is delivered to the customer, an input to the customer's process, e. a panel to make a car door, for further value adding. The problem is that once the order is entered, these process steps are fixed and typically could only be changed manually. Some of these processes have very limited locations in which the process can take place, however, not all. As an example, it is not uncommon to have to side trim a steel coil to its proper width. This can occur at several locations, both in-house and at an outside processor, OP. Next, consider all possible issues that could occur in the process over the course of those 3 months to cause delays, putting the supplier at risk of not delivering on time. For the sake of argument, let us assume the originally scheduled side trim process could not be done at the scheduled processor. A smart, interoperable system could parse this updated information and automatically reroute the side trim process to an OP with excess capacity that is on the way to the final customer to make up time. Our forecasting gets better the closer we get to the final event, weather prediction. Now, imagine an analogous case of a critical care situation with a compressed timeline medical transport. Is it possible, based instead of following the predefined procedure a particular ambulance service going to a particular hospital, we attempt to make better decisions based on the most currently available information? None of this can happen, however, without the entire supply chain exhibiting a certain level of interoperability. The transfer of information must also be secure. As a worst case, we don't want a malevolent agent using that same information to purposely reroute the ambulance for the purpose of putting the patient at risk. Knowledge gaps across cultural and geographical diversity. In this section, we examine the widening knowledge gap between areas that have highly skilled healthcare professionals and those areas that are underserved or are in need of improved healthcare solutions, as well as equally skilled professionals. Healthcare resources are inadequate, not well coordinated, nor allocated equitably, especially for people living in rural portions of the United States, which accounted for about 19% of the U.S. population in 2016. Access to programs and resources, including network connectivity, are exacerbated in rural areas due to geographic, demographic, and population density disparities. However, what is truly lacking is the data synthesis needed to improve outcomes to the single patient resolution. It is ironic that while we may be drowning in data, a smart hospital generates an estimated 5 terabytes of data/day. We have been unable to leverage that data to improve outcomes. Like any service/resource, rural areas are not good investments because of sparse population densities, higher poverty versus metropolitan areas, and greater number of uninsured. And because rural towns offer relatively fewer amenities in return, they are less likely to attract top talent. During practice, it can be difficult for healthcare providers to remain current and sharp since they are less likely to be exposed to the variety of cases seen from a larger population. It seems technology will be vital in closing gaps in these cases. Data-driven initiatives in healthcare are Healthy People 2030 and the National Academy of Engineering's Grand Challenge to Advance Health Informatics, Brock and Harris 2021. The former has a workgroup in Health Communication and Health Information Technology, HC/HIT. One objective of the HC/HIT workgroup is to increase the proportion of adults who use IT to track healthcare data or communicate with providers. The latter states health informatics should enhance the medical system's ability to analyze the comparative effectiveness of different approaches to therapy. In the UK, the Engineering and Sciences Research Council has a grand challenge expanding frontiers of physical intervention, which promotes effective interventions through the use of physical and digital devices for targeted approaches, RU 2020. Ultimately, if the clients cannot get to the healthcare, then the healthcare must be brought to the client. This will increasingly be through a tele-mode. Addressing accessibility, however, is only half the problem. A second issue is the cost, even if it were conventionally available, of delivering healthcare. For example, the state of Texas in the past decade has led the nation in the number of rural hospital closures, making up nearly 1/5 of all closures across the United States. This means patients must drive further to receive care. Those who are unable to drive themselves must rely on others for transportation. Ultimately, if clients can be better served, they will have increased knowledge and understanding of the benefits of healthcare, leading to behavioral changes that support long-term health, and also drive broader changes in policies and regulations related to decreasing healthcare disparities originating from knowledge gaps. Reduced collaboration knowledge transfer plays a major role in mitigating risks related to reduced collaboration and slowing innovation. Specifically, it has been well documented that collaboration and engagement with diverse perspectives enriches our results. Jardy, Webster, Petrinas, and Puig-Delval 2022. Whereas a lack of collaboration often leads to reduced knowledge sharing and even a widening of knowledge gaps. Analogy/example: sports teams are also required to mitigate these types of risks. Team collaboration and upfront preparation are essential in team sports like Formula One if the team manager, engineers, tire changers, and/or technicians are not trained and lack the proper knowledge in their specific function. This will adversely affect the overall team performance and will prevent the team from achieving strong results and ongoing best-in-class innovation. One mishap may lead to others, which eventually slows team competitiveness. A lack of communication and training also has the potential to destroy the overall team culture, therefore eliminating any chances of enduring strong organization values and greatness. This, in return, may result in reduced collaboration within the team and degradation in performance. Just like in Formula One, ensuring strong company values and adequate knowledge throughout a team is critical. There are several key elements that organizations should consider. Work with the right partners. An organization's culture and values should be the number one selection criterion. This may seem obvious, but it is often overlooked. It's important that organizations work with partners externally and internally that follow shared guiding principles and common core values. Working with an organization with the experience and required skills will also be essential. As an example, I've worked with organizations looking to adopt a company-wide healthcare system, and change management always seems to get deprioritized. This is an immediate red flag, and is almost always the wrong approach. Change management requires close interaction with the end users, and this is how organizations can really understand the voice of customer, EVOC, and to make sure that the system meets the end user's ultimate needs. Parker and Partridge 2021. If the system is unable to meet the needs of the end users, then the system has a high potential for failure even if the technology is stable and works perfectly. If there is not enough preparation and upfront scoping work completed in the early stages of an implementation, the technology may not be tailored to meet the needs of the end users, and end users are our most important customers. During the onboarding phase of the customer journey, it's critical that the deployment of advanced technology follows a methodological framework to achieve the desired results. Throughout the onboarding phase, working with a partner who acts as a trusted advisor can guide organizations looking to adopt company-wide systems through the end-to-end implementation with proper guidance and best practice knowledge. Almost always, these types of partners will leverage a proven methodology that has worked in the past and can be applied to other organizations looking to accomplish similar business needs. Follow a proven methodology or framework. Firms like BCG, Boston Consulting Group, KPMG, Klinveld Piet Marwig Gordeler, McKinsey, and PwC, PricewaterhouseCoopers, have gold standard frameworks and best practices that have worked for their clients in the past. These types of firms follow best practice guidelines that have been built over time, through many lessons learned. Typically, these types of implementations follow key phases with specified tasks and deliverables. For the purpose of this section, we will focus on the scope phase identified in the implementation framework. One caveat is that with new elements or change to context, best practices have to often be augmented or refined to address a new or expanded scope. At least they provide common knowledge and a reference point to reduce knowledge gaps. They are therefore valuable just for that and often more. Implementation Framework. Source: Sinzig Gosaro, 2022. In the scoping phase, establishing core guiding principles and/or North Star metrics will be crucial. This is where an organization will define what is most important to them. This may also involve understanding the day-to-day operations of the end users and understanding exactly how a specific technology will benefit them ultimately. The end users in business would like to understand WIFM, what's in it for me, and the KPIs, key performance indicators. Involving end users at the beginning stages of a project will support both the end users and the integrator/partner. For the end user, this gives them the opportunity to express their desires and needs. For the integrator/partner, this gives them the opportunity to assess how a specific technology can be configured and tailored to meet the end user's needs. This may relate to understanding where a new technology might fit into an existing business process, or how a technology can be tailored to a specific use case. Ultimately, involving end users early on is essential for mitigating the potential for knowledge gaps. Building quantifiable metrics will be important for the business to make key decisions. Defining the acceptance criteria and KPI metrics that customers are looking to achieve will be essential. As part of a global augmented reality training implementation for a global medical device manufacturer, our ultimate business goal was to increase operator productivity. So we prioritized ramp rate to medical device yield production. This was the key to getting out of technology pilot purgatory, and the technology rollout resulted in widespread value to the medical device manufacturer globally. After establishing the core KPIs and proving that the system met the customer's objectives, our ultimate goal was to ensure that we optimized the solution with a core focus on adoption for the end users. This led to widespread end-user advocacy for the system. Path to Advocacy Framework. Source: Sinzig Gosaro, 2022. Measuring Knowledge Transfer Success. Measuring success is where the rubber meets the road. Knowledge transfer success should be monitored on a regular basis and covered with close executive alignment on a quarterly or semi-annual basis. Executive Business Reviews, EBRs, will help organizations realize the success of closing knowledge gaps. This is where key stakeholders have transparent discussions regarding goals against the key outcomes defined in the scoping phase. EBRs also provide the opportunity for the key stakeholders to align on what is, and what is not, working, and to be proactive about fixing what needs to be changed in order to meet the desired outcome. These quarterly/semi-annual health checks will now become one of the key drivers for long-term success. Now that there is an understanding of the key North Star KPIs that make a technology transformation successful, it's just as important that the end users understand how to utilize this technology. Does the fact that I don't know how something works change the effectiveness of that thing? Ignorance is not bliss. There are several examples in industry where it has been seen as desirable to develop vision terms or marketing representation terms before the details are hammered out. While this is acceptable in consumer technology, it is less desirable in medical technology since all stakeholders in the supply chain would then be relying upon practical details or the absence of them to actually make things work. Therefore, if your outcome depends on the chain of elements that make up all the activities or technologies needed to drive the outcome, we would advise that you need to understand how things work. If you don't know how something works, you can't evaluate its effectiveness. If you are beholden to a quality level by some important stakeholder, then you better know how everything in the bill of materials, BOM, works. However, this can be harder than it sounds due to the complexity and multiple dependencies of a lot of systems in current use. That's why future systems need to be purpose-built with an eye toward the ability to drive a BOM. Could there be some temporal aspect about knowledge gap reduction? It is possible for a knowledge gap to be reduced or closed only temporarily while allowing a user to complete some useful task. In healthcare, an example of this is the use of an automated external defibrillator, AED. The purpose of an AED is to deliver a life-saving or preserving electric shock to those in cardiac arrest. However, a user does not necessarily need a priori knowledge of human physiology to operate the device any more than a licensed driver needs knowledge of an internal combustion engine to operate a vehicle. The device, AED, itself acts as a supervisor of a human-in-the-loop, closed, cyber-physical system to determine and influence efficacy, cobots. As a corollary, we discuss, compare, contrast knowledge gaps with skills gaps. For example, the university where one co-author is Engineering Technology Department Chair and faculty promotes applied learning experiences, ALEs, which are transformative learning experiences designed to engage students in active and reflective learning to further develop beyond disciplinary skills and expand students' perspectives of self, community, and global environments. https://www.tarleton.edu/al/index HTML. During the spring 2018 semester, faculty engaged with an instructor from the School of Kinesiology to establish an ALE. It combined students in kinesiology studying therapeutic rehabilitation with engineering technology students studying machine design and/or embedded systems to produce assistive technology designs. It brought together such a disparate group of students, allowing them to work in an area and with people they might not have known existed previously and to build empathy for one another. Moreover, it exposed students to the political, social, and economic issues resulting from debilitating diseases and injuries such as equal access, affordable health care, and job retraining and retention. It is probably the most true-to-work experience I've been a part of. Finally, the students deserve a lot of credit for making the projects generally work even though we were unable to structure time for them as part of the classes. This DEI practice builds empathy for those who stand to gain from developments. It also builds allies with those who have to work together despite their disparate backgrounds. How much do I need to know about something before I can declare the knowledge gap to be closed? Knowledge gaps should never be considered closed. Because things are always changing, there can be unknown impacts on technical systems whether those changes are in tooling, standards, or regulations. Expect change and expect there to be knowledge gaps. What this means in our minds is that you need to be diligent in cultivating multidisciplinary teams. You need to have high-performing, highly functioning communities of practice where experts from different areas can learn from one another, constantly and on an ongoing basis. Our physician educator co-author, Dr. Felix Enkel calls this a nomad, Wang, Schleigwein, Csis Kekmanovic, and Kaelane 2020. While knowledge gaps can never be closed, if you are repeatedly asked by leaders in multiple segments to explain topics, you can comfortably imagine that you're considered a leader in that domain. Being a leader doesn't mean you've closed all knowledge gaps. Being a leader means you are aware of them, including the presence of your own gaps, and that you have developed robust systems and networks to address them on an ongoing basis. For example, the world is constantly changing and technology is changing faster than most things. Today's experts will be outdated in few years if they won't keep learning and updating their knowledge. It was true several years ago, but it is even more significant today, some years into COVID. It seems that COVID expedited many areas, squeezing processes that would have taken 1-2 years. Companies that managed to evolve and adapt made it big time, while others ceased to exist. Specifically, the technology sector has made a huge leap, from technological to HR issues, such as remote work. Whereas we examine reducing risks in the healthcare industry, we must remain adaptive and flexible in our desire to remove barriers and close knowledge gaps. Reducing risks in healthcare. Just as there is nothing that is 100% secure, can we assume that risks cannot be eliminated? That said, we should seek to identify risks, weigh or measure those risks, and prepare to mitigate those risks. Considering that acceptable and unacceptable risks are ultimately determined either directly or indirectly by a human, the identification of risks is subjective. This might be characterized with being an individual who is risk-tolerant or risk-averse. When considering a risk as acceptable, first decide if it is an acceptable reality, if that risk becomes realized. Consider also that if knowledge gaps are reduced, the perception of risks will change. Are people with less knowledge of something more likely to take risks, or would the lack of knowledge make them more fearful of taking risks? Reducing knowledge gaps and encouraging behaviors to reduce gaps. When discussing knowledge gaps, there are some important traits and behaviors that we need to recognize and embrace as it relates to establishing a foundation from which we can listen, empathize, and reflect. That said, listening skills are as equally important as communication skills, speaking and writing. Whereas, being able to establish empathy with a need as conveyed by a person or organization is the first step in building an understanding of needs. From there, we are able to establish a feedback loop of listening, asking questions, and reflecting on what has been conveyed and gathered from the stakeholder, thus ensuring that we don't start to work with limited information, incorrect assumptions, and without personal biases that negatively influence our perception of what is needed and what we are solving for. Demystifying technology/relatable tech. The proposal that technology can be demystified triggers some basic thoughts related to how we might go about explaining technology in relatable terms and to what extent we should seek to demystify technology. For example, as we have proposed in previous content, a person does not need to know about the inner workings of an automobile in order to effectively operate a vehicle. Similarly, a patient doesn't need to know everything down to the cellular level of healthcare in order to lead a healthy and happy life. However, in healthcare, ignorance is not blissful, where the more a patient knows about their own healthcare, the more they can advocate for themselves. For example, there are many technologies available to patients that can be used to determine their general health, blood pressure, blood oxygen levels, pulse rate, temperature, cardiac rhythm, etc. But do patients understand how an alignment of the data from those technologies might paint a more detailed picture of their health state versus not aggregating all of the data, specifically at the point that the entire data set intersects? Probably not. So, if we are the patient looking to augment our healthcare knowledge and our understanding of healthcare-related technology, where do we go? If you can't explain it simply, you don't understand it well enough. Albert Einstein: How do gaps in general knowledge influence/impact/expose risks in the medical industry? Many individuals accept that there will be gaps in knowledge between a healthcare professional and that of a patient. In some extreme cases, that acceptance has resulted in healthcare professionals who will not directly interact with a patient. Thus, we widen the knowledge gap and risk negatively impacting the quality of care that a patient is afforded. That said, we believe that behaviors associated with empathy, speaking in relatable terms, and collaboration are key elements that could increase or decrease knowledge gaps. An actual example, associated with collaboration, was exposed during visits to both neuro and cardiac surgical suites, where it was obvious that surgical prep methods and best practices are not shared. Specifically, something as simple as intelligently preparing a patient's gowning/draping, wrapping versus stapled to a patient, represents just one small element that may impact a patient's overall care. Additionally, lack of empathy for a patient's needs versus a doctor's perception of those needs could mean that something has been missed/ignored. That something also represents a gap in knowledge that may manifest as undesired results and ultimately reduce a patient's quality of care. Closing the gap between a doctor's knowledge and that of a patient represents a critical element in demystifying healthcare. Specifically, learning to speak in terms with which a patient can relate will help the patient make more informed decisions. Conversely, patients who do not know or understand what is needed before and after surgery may make decisions that are fatal. With that point in mind, patients can do their part in closing knowledge gaps by not fueling organizations and individuals who do not possess certifiable skills in healthcare. In short, patients looking to increase their knowledge of healthcare should ensure that the material they are reading is backed up by evidence, such as found with empirical peer-reviewed research and scientific discovery. Knowledge transfer use case/example: sometimes a point is not easy to relate to, so we practice a belief that it is better to show someone something than to tell them about it. That said, even if you were not alive or directly involved in the Challenger shuttle accident, we are confident that you have heard about the event. So, when we speak about the accident, we are certain that most people know what happened and even how the accident changed many things at NASA, National Aeronautics and Space Administration. But what might not be clear is how the event can be linked directly to the concept of knowledge gaps. Space Shuttle clip art, free to use, public domain. Source: retrieved from https://www.clipart/max/m2i8h7m2h7b1b1 and 4/Space Shuttle Challenger accident results of failed knowledge transfer. It is not always the case that gaps in knowledge can lead to disaster, but instead it is the inability to transfer knowledge in a relatable form that can lead to disaster. Further, if knowledge is not conveyed in usable form, then the resulting confusion/misinformation can widen knowledge gaps, which can have disastrous results. Take for example the 1986 Challenger shuttle accident, where those who possessed the knowledge and those who controlled the decision to launch were unable to communicate or transfer knowledge in such a way as to avoid the accident. Specifically, though it was perceived that the conditions surrounding the launch were within the margins of a no-go scenario, the information related to how those conditions might impact the shuttle were not conveyed in a way that enabled leaders to make the right decision. Of course, without focusing blame on any one group or individual and speaking from experience as a co-author and person who was working at Cape Canaveral in the 1980s. The Challenger accident does point to problems where it is not always the lack of knowledge that results in adverse effects. That said, we not only need to consider the lack of useful knowledge, but we also must examine the way in which we transfer knowledge. Abdallah, Renakapa, and Suresh 2022. Using the Challenger accident as an example of how knowledge gaps form or can be widened, we must first seek to share knowledge and then find ways to convey that knowledge. Keeping in mind that we all want to be understood, it is not enough to convey knowledge as we perceive it, but to understand how others need to receive knowledge in such a way as it becomes relatable or useful. That point is easily illustrated when we observe the reaction of individuals with whom we are speaking, transferring knowledge. If they make gestures that the information went over their head, then the issue is not with them, but instead with us, the owner of specific knowledge. Thus, we must then look for other ways to convey knowledge through a process that involves developing empathy with the target of our knowledge transfer. For example, consider the background, experiences, education, etc. of the target and seek to use that information to reshape the knowledge into a form with which the target can relate. At the same time, learners have to take responsibility for their own learning agility, performance, and commitment. It's a two-way street and the whole burden isn't on the person with the knowledge. All workforce members, in particular leaders, need to train and challenge themselves to be the highest level of learning athlete available to them intellectually and practically. This is both in rapidity and complexity of how multiple disciplines intersect related to essential medical technology details. Swim lanes, or building team alignment and synergy, healthcare organizations comprise numerous divisions, departments, and teams responsible for addressing the requirements for networking and IT functions, security, building operations, asset tracking, medical device security, and desktop and mobile device management, just to name but a few. While each has a specific mission, the mission of the overall healthcare organization can often be missed. The mission of individual groups may even overlap, leading to duplicate effort and expense or be executed in a manner which is counterproductive to other teams. It may be obvious that a more ideal approach is one where the organization has clear roles and objectives that reduce duplication and encourage collaboration between teams for optimal outcomes. But this synergistic ecosystem often requires top-down sponsorship to recognize and help define individual team goals and promote engagement of the different stakeholders on a regular basis. These periodic check-ins enable each team to share knowledge regarding their individual contributions and progress toward the overarching mission statement. Such ideals can certainly apply to any organization, but healthcare uniquely struggles with these challenges due to the diverse and organic evolution of the network, connected devices, and applications, many that are introduced by numerous stakeholders, including medical staff. For example, a doctor may add a group of new clinical devices and applications not vetted by the IT, security, and server/application teams. In stark contrast, a typical financial institution consists of a much more homogeneous environment with a central team that mandates a common desktop, mobile, and application environment. IoT devices are more likely to be from a single or limited set of vendors, and new devices are closely scrutinized and denied by default. Understanding the diverse makeup of your healthcare organization's people and devices can raise awareness into potential blockers and bottlenecks in achieving critical goals such as clinical device security to ensure reliable services without compromising patient safety or privacy. Multiple teams play pivotal roles in achieving this goal. from Healthcare Technology Management, HTM, sometimes referred to as clinical engineering or biomedical engineering, to information technology, IT, security, facilities, desktop management, server/application, medical device manufacturers, MDMs, and others. With so many teams playing a role in clinical device security, it is easy to see how responsibilities can blur due to overlap or worse, be neglected. Let us take a common scenario seen in different organizations. The HTM team is focused on ensuring all clinical IoT devices are tracked, assessed for bugs, vulnerabilities, and risk, and ensuring they are updated with the latest security software and patches. In some cases, they cannot be patched and therefore represent a higher risk and exposure to potential compromise. At the same time, the physical security, or possibly the facilities team depending on your organization, may be tasked to track all cameras and their software, including those used in a medical setting such as patient or surgical rooms. The IT team is tasked with ensuring network connectivity and often manages the Network Access Control (NAC) system for all connected devices, both medical and non-medical. The security team sets policy and may also manage the organization's firewalls and other security devices. Still, many other teams are playing a key role in this scenario. It is not uncommon for HTM, IT, and security teams in this example to have unique objectives and expectations. Looking at your own organization, how often do your respective teams meet to discuss their roles, coverage, and key projects? Do they collaborate and know the main contacts responsible for critical services across the virtual divide? Or would the response from one group more likely be "we don't work with that team," or "that is not our job"? If the answer is the latter, then see this as an opportunity to unlock your organization's full potential. Even if teams are not outright dismissive of the other, passive-aggressive behavior can disrupt and even halt progress for major initiatives. This is where top-down sponsorship can drive common vision and outcomes and promote collaboration to overcome obstacles. Using the previous example, the HTM team's work to secure and patch vulnerable devices is certainly important, but it is also just as critical that the IT team secure network access to allow only trustworthy devices and limit their exposure to potential internal threats. Simultaneously, the security team must implement the proper controls on the traffic to gateways, internal servers, and external systems. By securing the borders and internal communications, the risk to vulnerable medical systems is greatly reduced, and patching helps ensure systems are not compromised even if unauthorized traffic makes its way to the device. Recognize that the complementary efforts can help foster an environment of mutual respect and collaboration, and influence teams to offer support in areas that optimize results. Furthermore, it is important to recognize the ideas and the value each team and its members bring to the table. This recognition encourages new ideas and solutions to problems while increasing employee satisfaction and well-being. Dysfunctional clinical IoT device security teams. Source: HIPS, ORDR Incorporated. High-functioning clinical IoT device security team. Source: HIPS, ORDR Incorporated. Establishing a consistent set of terms and definitions is equally important when defining roles and responsibilities. While the taxonomy used across different organizations may differ, focus should be on ensuring all teams within your organization abide by the same set of terms. Align teams such that there is a common understanding as to which team is lead, or has primary responsibility for a topic, which team or teams have a secondary or supportive roles, and those which may perform a consultative role. Security terms which merit clear definition and role assignment include trust, identity, authentication, authorization, access control, privacy, safety, protection, operations, audit, and interoperability. Roles can be use case specific such that identity for connected medical devices may be handled by one team, identity for non-medical another, and identity for servers and medical applications yet another team. In general, security policy itself should be centralized as it sets governance for the entire organization. Similarly, privacy policy should be centralized. However, the execution of security and privacy policy can be led by individual teams responsible for a specific aspect of the security architecture. The following provides a list of related terms aligned by topic which must be commonly understood across teams as well as each team's primary/leading, secondary/supporting, or consultative/feedback role. Security policy: integrity, availability, authenticity, privacy/confidentiality controls security processes, practices, and principles. Privacy/confidentiality policy: data sharing, regulatory compliance, regional accommodations, privacy processes, practices, and principles. Trust, authorization, access controls, access rights and permissions, role-based access control, RBAC, enforcement, segmentation policy, decisions, identity, authentication, identity stores, credentialing certificates, X. 509, PKI for identity, trust stores, etc. Unique ID, UID, safety hazards and harms mitigation requirements, effectiveness, safety, risk management, intended use and use environment, interoperability, integration, testing, traceability, syntax, semantics, transformation. Again, a common agreement on terminology and team alignment can help ensure critical functions are properly covered, eliminate gaps and confusion, and optimize the contributions and outcome of the entire organization. Large healthcare organizations are often hindered by separate, monolithic tools and processes. For example, within your organization, is there a standard process to onboard new clinical devices? Is the device properly tracked in a system visible to the HTM, facilities, security, and IT teams? Due to the convergence and interdependence of the different teams, holding data hostage to a given team is often counterproductive. Having separate tools and processes itself can be extremely costly in terms of licensing, deployment, and professional services, and make the system less useful if data cannot be shared between systems. Through organic growth, mergers, and acquisitions, many healthcare systems are composed of siloed applications with their own set of infrastructure, servers, and teams to manage. Here is yet another opportunity to streamline operations and foster interoperability and collaboration based on tool selection that serves the needs of the overall organization rather than individual teams. Of course, there are cases where the benefits derived from a special application merit its limited use to a specific team, but it is important to recognize opportunities to converge resources that will elicit greater benefit to the organization and its core mission. This can be particularly challenging as budgets tend to be granted to specific teams, and therefore may suppress altruistic behavior. This is where leadership can help execute on a common good. To ensure proper coverage, the clear definition of roles and responsibilities can prevent gaps in clinical device security. As cited earlier, if there is a camera that is used in a clinical setting, there should be no confusion as to which team is responsible for its maintenance and security upkeep. Similarly, is a nurse call device managed as a medical device or media device? Is a workstation or mobile device that is used to transmit patient data managed by HTM or the desktop/mobile management team? Ensuring clearly defined coverage and roles will help ensure teams are synchronized and potential gaps eliminated. In summary, look inside your organization and objectively assess their level of collaboration and mutual understanding of roles, coverage, and unique capabilities to support other teams and the overall goals of the organization to deliver the highest possible outcomes. Like a swim team, maintaining swim lanes can help ensure there is no disruption to other teams or team members, but like a relay, it is the collective efforts that enable the organization to succeed. Hitchcock and Stavros, 2017. Cognitive approach to understanding and motivating knowledge sharing. Effective knowledge sharing as well as collaborative and innovative engagements are built on the foundation of autonomous motivation, which embraces an alignment of ideas from individuals who come from multidisciplinary and diverse backgrounds, cooperatively involved in creating technologically advanced solutions. Likewise, though motivation theory encompasses various concepts, including a motivation, lacking the ability to recognize positive outcomes associated with action, the focus is on the use of motivational concepts that are associated with self-determination theory, SDT. Accordingly, it is proposed that the motivational theories characterized within SDT are autonomous, controlled, extrinsic, and intrinsic motivation. Whereas, a discussion of autonomous motivation is more closely aligned with the prosocial behavioral characteristics that promote an individual's freedom to choose, while exhibiting moral and ethical attributes toward other individuals. With that in mind, it is postulated that individuals who display autonomous motivational behavior are able to effectively share knowledge, collaborate technologically advanced and innovative concepts, resulting in better outcomes and improved satisfaction, while realizing increased psychological well-being. Conversely, though traditional collaborative theories focus on anticipating and resolving interorganizational conflicts, we examined the desired motivational concepts that reflect the constructive qualities of each collaborative participant. Further, with consideration for realizing effective collaborations and knowledge sharing, the positive attributes associated with psychoanalytic transference, improved collaborative bonds that support positive experiences, are embraced as foundational concepts that align the theories of autonomous motivation and collaboration, specifically, with a focus on the motivational characteristics of participants' independence, constructive results, and mutual accountability within collaborative groups that are oriented toward a common goal. Gray, 1989. That said, let us examine a little more closely both motivation and collaboration theory, as we explore improved methods for knowledge sharing. Motivation theory. Motivation theory encompasses a number of theoretical concepts, autonomous, controlled, extrinsic, intrinsic, but when viewed through the lens of SDT, individual motivation is transformed into a cognitive process of self-actualization and psychological well-being. Deci and Ryan, 2008a. That being considered, motivation theory is a concept and process found within sociocultural environments, where an individual's behavior is both externally and internally influenced, as exhibited through needs and desires. Regardless of potential influences from an individual's cultural environment, autonomous motivation will produce the greatest personal satisfaction while maintaining a healthy mind and body. Accordingly, Chen and Zhang, 2010, infer that individuals who maintain constant awareness of motivational types while embracing a vacillating balance between intrinsic and extrinsic motivational influences will experience a greater sense of well-being, where they have chosen to be productive and socially responsible individuals. Collaboration theory. Garrison, Anderson, and Archer, 1999, describe collaboration as concept that is not focused on simple exchanges, such as guided by the injection of specific declarative instructions, but as shared experiences between participants that are constructive and result in the creation of knowledge. Thus, collaboration is both a conscious and unconscious process that aggregates cognition with sociocultural development from the perspective of reaching a balance between psychological and sociological constructs. Gaida S. 2004, proposal that collaboration is a journey, not a destination, p. supports the idea that collaboration theory represents an understanding of how individuals cooperatively engage in work to achieve a shared goal that embraces mutual accountability. That said, collaboration across interorganizational environments, i.e. business units, departments, and locations, empowers individuals to align on long-short-term innovative solutions and goals that could not be realized through individual convergent thinking, working alone or independently. Comparison of collaboration and motivation theories. There is a causal relationship between motivation and collaboration, where the success of collaborative efforts is dependent on the motivational level of the participants who seek to move from focusing on individual work to tasks that focus on common shared goals, where making a difference is a driving factor. Specifically, effective collaboration cannot exist unless participants, problem statement owners, and leadership are properly motivated to trust collaborative processes, where job titles and egos should be set aside. From those statements, an examination of collaboration with respect to motivation exposes that effective collaboration cannot be realized unless participants are properly motivated, autonomous motivation. Correspondingly, the key or binding element that inspires successful collaboration and encourages desired motivation is skilled facilitation and mentoring, which serves to promote attributes of professional growth. Aligning collaboration and motivation theories. The theories of collaboration and motivation appear to be only vaguely aligned. Where collaboration implies cooperative engagement and motivation is principally evaluated through the lens of the individual. However, it is posited that within technologically innovative environments, where socio-cultural influences focus on developing prosocial behavior, individuals who are both extrinsically and intrinsically motivated, autonomous, are able to more easily align their goals within collaborative efforts. Similarly, individuals who seek to be collaborative from the perspective of increasing knowledge, where greater satisfaction is often derived from the journey toward their goal, possess aspirational alignment with the theory of autonomous motivation and intrinsic desires. Controlled motivation approaches collaborative efforts from the perspective of extrinsically influencing individuals to engage in alliances, such that avoidance of punishment, guilt, and competition are the principal motivating factors. As is inferred by Cohn, 1999, incentivizing negative and positive collaboration among employees, where individuals are manipulated into working together, may have worked during the Industrial Revolution, but it is an ineffective method such that it eventually leads to failure and harm to employees' morale. Thus, from the perspective of collaboration, the more artificial inducements that are used to motivate people, the more they lose interest in what they are being bribed to do. Cohn 1999, p. All things considered, successful knowledge sharing and innovative collaboration focused on integrating technology, with resultant long-term interorganizational alliances, can only be achieved when individuals possess the self-realized freedom to choose and act on those choices in directly connecting collaboration and goal-related successes with personal satisfaction. Thus, it is proposed that individuals who exhibit the characteristics of autonomous motivation, such as those characteristics that demonstrate the behavioral attributes of self-discovery and persistence, are the individuals who are more apt to effectively collaborate in creating innovative and novel technological solutions that are able to interoperably exchange and transform data. Interoperability and technology integration. What is the purpose of interoperability in healthcare, and do knowledge gaps affect it? What is the current state, and how can we drive toward an ideal state? So, when thinking in terms of interoperability and more specifically technology integration, are we considering the aggregation and the transformation of data through the lens of an attribute's availability versus utility? Additionally, when thinking of interoperability, shouldn't we be considering data security needs such as those represented by the IEEE/UL TIPS, trust, identity, privacy, protection, safety, and security standard principles? Accordingly, there are critical attributes of interoperability that need to be considered, i.e., scalability, governance, conformity, compliance, integrity, quality, accuracy, reliability, reproducibility, and compatibility. For example, some of the use cases that we believe should be considered when discussing interoperability might be continuous glucose monitoring, CGM, design, deployment, and use, and it would be good to consider the use case of the connected IoT home that can be classified as the home healthcare. That point should emphasize that classic EMRS and EHRS band-aid approaches are from the perspective of an advanced technologist considered to be outdated, as HL7 methods are for accomplishing ideal interoperability while exposing that interoperability should address the needs of patients, healthcare professionals, the payer, and the non-professional caregiver. Considerations and risks. Interoperability assumes that technology acceptance should evaluate technology and social aspects to identify methods for technology integration, while also considering 5 factors that influence technology adoption: technology quality, integration management, solution ease of use and usability, impact on institutional development, sustainability. The combination of these 5 factors is appropriate at any phase of integration, assessment, decision-making, adoption, design, development, deployment, and sustainability, where the concept of solution interoperability embodies human, hardware, and software influencers, respectively. Though EHRs and EMRs originated as a billing solution, most organizations view EHRs and EMRs as their interoperability solution. However, that point was missed during the implementation of EHRs and EMRs, where technology int. That is the heart of advanced health technology. If it helped, a quick subscribe keeps more summaries coming. So how do data and technology connect? That is exactly where we started. Go back to the top and watch it click into place.